In episode 60, titled Encoding Categorical Data, One-Hot versus Label Encoding Trade-Offs, the goal is to encode categories correctly so models interpret them safely, because the encoding step is where you create numeric meaning out of labels. A category label is not inherently mathematical, but most models operate on numbers, so the way you translate labels into numbers determines what relationships the model is allowed to assume. The exam cares because encoding errors are subtle, common, and highly consequential, especially when codes look numeric and invite false interpretation. In real systems, encoding is also a governance issue because it affects explainability, stability, and how models behave when new categories appear. If you learn the trade-offs between one-hot and label encoding, you can match representation to model assumptions instead of accidentally injecting fictional geometry into your feature space. Good encoding is not about preference. It is about choosing what meaning the model is permitted to learn. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
One-hot encoding represents each category as its own indicator feature, meaning a field with k categories becomes k separate binary columns, where exactly one is active for a given record. The main advantage is that it does not impose an artificial order or distance between categories, because each category gets its own independent representation. In this structure, the model can learn a separate effect for each category relative to a reference, and changes in one category do not imply any numeric relationship to another category. One-hot encoding is conceptually aligned with nominal categories like region, device family, department, and product line, where category values are labels rather than levels on a scale. The exam expects you to understand that one-hot encoding expands dimensionality, which can create sparsity, but it also protects you from false numeric assumptions. When you narrate one-hot encoding, you are describing a representation that treats categories as distinct flags rather than as numbers with arithmetic meaning. Label encoding assigns numeric codes to categories, such as mapping each label to an integer, and it is tempting because it is simple and compact. The key issue is that the numbers are arbitrary identifiers, not measurements, but many models treat numeric values as ordered and distance-based by default. If you encode categories as 1, 2, 3, and so on, you risk allowing the model to interpret Category 3 as greater than Category 1 or closer to Category 4, even though that ordering is fictional. Label encoding is sometimes acceptable when the model treats categories as unordered symbols internally, or when you explicitly use the codes only as keys for lookup rather than as magnitudes. The exam often uses label encoding as a trap because it looks like an efficient solution while quietly injecting false structure. When you describe label encoding clearly, you emphasize that it is a mapping for representation, not a claim that the codes carry distance or order.
One-hot encoding is the safer default when category order has no meaning, because it prevents the model from learning relationships based on the numeric code rather than on the category identity. If a feature is nominal, such as city, operating system family, or incident type, there is no sense in which one category is inherently higher or lower, so any numeric ordering would be arbitrary. One-hot encoding expresses exactly that. Categories are different, not ordered, and the model must learn their effects separately. The trade-off is that one-hot can inflate dimensionality, especially when the number of categories is large, which affects memory, training time, and overfitting risk. The exam expects you to balance this by recognizing when one-hot is necessary for correctness and when high cardinality demands additional strategies. The key reasoning is that correctness comes first. Efficiency can be optimized after you choose a representation that does not create false meaning. When order exists and spacing is unclear, ordinal encoding is appropriate because it respects rank without pretending that the steps are equal in magnitude. Ordinal encoding maps ordered levels such as low, medium, high to increasing codes, preserving order so the model can learn monotonic relationships if they exist. The caution is that the model may still treat differences between codes as equal increments, so you should interpret coefficients carefully and consider whether the modeling approach can represent non-uniform spacing across levels. The exam cares because it tests whether you recognize that ordinal variables are neither purely categorical nor fully continuous, and the encoding should reflect that middle ground. Ordinal encoding is most defensible when the order is meaningful and consistent, but you should avoid assigning ordinal codes to nominal categories because that creates artificial order. When you narrate ordinal encoding, you are saying that higher levels represent more of something, even if the exact quantitative gap between levels is not defined.
A major risk of label encoding for nominal data is that it can create false distance and bias, especially in models that rely on numeric comparisons or distance metrics. If the model sees category codes as numbers, it can split or weight based on their magnitude, which effectively groups categories by code rather than by meaning. This can create spurious patterns, like a model that treats categories with higher codes as higher risk simply because the mapping happened to assign high codes to categories that appeared more often in the training data. It can also create unstable behavior because changing the mapping order changes the numerical structure the model sees, which can change results even though the underlying data did not change. The exam often tests this by presenting category codes and asking what encoding is appropriate, and the correct answer is to avoid numeric coded relationships unless the order is real.
When you explain this risk, you are explaining why encoding is not a cosmetic step. It can change what the model is allowed to learn and therefore what conclusions it produces.
High-cardinality categories, meaning features with many distinct values, require special handling because one-hot encoding can create a very wide, sparse matrix that is expensive and prone to overfitting to rare categories. A practical approach is grouping, where you merge rare categories into an other bucket, preserving the most common categories while reducing sparsity and improving statistical support per category. Hashing can also be used to map many categories into a fixed number of buckets, reducing dimensionality while accepting collisions as a controlled trade-off.
Embeddings provide a dense representation that can capture similarity structure between categories if such structure exists, and they are common in neural approaches where the model can learn a useful low-dimensional space.
The exam expects you to know that these methods address representation scale, not just modeling preference, because high cardinality is a data structure constraint. When you narrate these strategies, you are describing how to keep categorical information without turning the feature space into a mostly empty ocean of indicators.
Rare category explosion is a specific hazard where the encoding creates many features that appear only a handful of times, which harms generalization because the model can memorize those rare patterns without learning durable structure. In one-hot form, a rare category creates a column that is almost always 0 and occasionally 1, and the model can assign it a large weight based on very few observations. This looks like strong signal in training, but often fails in validation because the rare category appears differently or not at all, and it can create unstable coefficients and inflated confidence. Rare category explosion also increases sparsity and computational overhead, which can slow training and lead teams to cut corners in validation. The exam tests this by describing data sets with many unique categories and asking what risk or mitigation applies, and the right reasoning is to reduce sparsity or apply regularization and grouping. When you describe rare category explosion, you are warning that the representation has created too many degrees of freedom relative to evidence. Choosing encoding by model type is an exam-relevant decision because different model families respond differently to categorical representations. Linear models typically require one-hot encoding for nominal categories because they treat numeric inputs as ordered and distance-based, and one-hot is the clean way to represent separate category effects. Tree-based models can sometimes handle label-encoded categories better than linear models because they split on thresholds. But threshold splits on arbitrary codes still impose a fictitious order, so you should be cautious unless the implementation treats categories as unordered or you use one-hot for safety. Neural models often benefit from embeddings for high-cardinality categories because embeddings provide compact, dense representations and can share statistical strength across categories through learned similarity. The exam is not asking you to memorize every algorithm's quirks. It is testing whether you align encoding to the assumptions the model will make when it sees numbers. When you narrate this, you show that representation and model are a coupled design choice, not independent decisions. Consistency between training and inference encoding is essential because a model can only interpret inputs correctly if the mapping from categories to encoded values is stable. If the mapping changes, a category that was represented by one indicator during training could be represented differently during inference, which effectively scrambles the input meaning and degrades performance. The practical safeguard is to save the mapping or encoding scheme used during training and apply the same transformation to new data, ensuring that category-to-feature alignment is preserved. This matters especially for one-hot encoding, where the set and order of columns must be consistent, and for label encoding, where the numeric code must map to the same category identity. The exam often frames this as deployment consistency or pipeline reproducibility, and the correct reasoning is that encoding is part of the model, not a separable pre-step. When you treat encoding as a saved artifact, you reduce deployment failures and make evaluation results meaningful.
Unseen categories at inference are inevitable in many systems, especially when categories are tied to evolving products, new user behaviors, or external identifiers.
A safe fallback rule is necessary so the system can handle unknown values without crashing or assigning arbitrary numeric codes that introduce unpredictable behavior.
One-hot approaches often use an other bucket or all-zero encoding with an explicit unknown indicator, while label encoding can map unseen categories to a reserved code that the model was trained to interpret as unknown.
The key is that the fallback should be planned and evaluated because unknowns can be frequent in drift scenarios and can concentrate in certain segments, affecting fairness and performance.
The exam may describe new categories appearing post-deployment and ask what to do, and the correct answer includes a safe handling strategy rather than assuming the category set is closed.
When you narrate unseen category handling, you are emphasizing robustness. The model must behave sensibly when the world changes.
Encoding choices should be documented to support explainability and governance because encoding affects what the model's coefficients or feature importance actually mean. With one-hot encoding, each indicator has a clear interpretation as membership in a category, while with hashing or embeddings, interpretation becomes more abstract and may require different explanation approaches. Documentation should include what encoding was used, why it was chosen, how rare categories were handled, how unknown categories are processed, and how mappings are versioned over time. The exam treats this as part of responsible model development because stakeholders need traceability to trust automated decisions. Documentation also supports reproducibility because retraining without consistent encoding definitions can create silent shifts that look like model drift. When you document encoding, you make the representation explicit, and that reduces the chance that a future change introduces hidden bias or breaks deployment.
A useful anchor memory is encoding creates meaning, so choose meaning deliberately. Encoding is the step where labels become numbers, and numbers invite models to assume order, distance, and comparability unless you constrain those assumptions. Choosing meaning deliberately means deciding whether categories should be treated as distinct flags, ordered levels, hashed buckets, or learned embeddings based on what the category represents and what the model family assumes. The anchor helps on the exam because it pushes you away from convenience-based answers and toward representation-based reasoning, which is what the questions are really testing. It also helps in practice because it reminds you that encoding is a design choice that must be aligned with both data properties and governance requirements. When you keep the anchor in mind, you naturally ask what interpretation the encoding implies and whether that interpretation is valid. To conclude episode 60, choose encoding for one field and explain why, because this is the clearest way to demonstrate you can match representation to meaning and model assumptions. Suppose the field is incident type, which is a nominal category describing kinds of events with no inherent order, and you plan to use a linear model for prediction and explanation. One-hot encoding is the appropriate choice because it represents each incident type as a separate indicator without imposing artificial order or distance between types. You would also handle rare types by grouping them into an other bucket to reduce sparsity, and you would save the mapping so training and inference use identical columns. This choice is defensible because it preserves the label nature of the field, supports stable interpretation, and avoids the false numeric meaning that label encoding would introduce. When you can explain encoding this way, you demonstrate exam-ready judgment that protects both model validity and operational reliability.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.